Here's a diagram illustrating a concept that you probably learned at some point in high school. So we have time on the x-axis, and on the y-axis we have distance. And so you can imagine here, maybe we're throwing a baseball, and when the ball leaves your hand, or you can think maybe you're kicking a soccer ball if you prefer soccer, the moment the ball is released or it's kicked, it covers a lot of distance, but over time it loses energy, and the distance that it travels is increasing, but at a decreasing rate until it's flat, right here where it's flat. Now suppose we wanted to know what the average rate of change of this. I'll pick one. I'm from Toronto, so I'm going to pick baseball. So imagine we're throwing a baseball, we're throwing a ball, and we want to know how far that ball traveled, say from x1 to x2. So what's the average distance traveled? And we know that the distance is going to be f of x1 after x1 time, and the distance is going to be f of x2 after x2 amount of time. And so the average rate of change here is going to be f of x2 minus f of x1 over x2 minus x1. So there's a couple different ways we could look at this. I could imagine their numbers. Maybe the distance that the ball traveled is going to be, maybe 90 feet minus 50 feet when it goes from 4 to 2 seconds. And we get something like an average rate of change of 20. What will we call the average rate of change if we're talking about time and distance? What's the average rate of change? Well, this would be the speed, right? So maybe it would be feet. That's imperial units of distance, feet per second. Something like that. And so that's an average rate of change that you're used to. We could change this a little bit. So I'll delete what we've got here. I'll delete that. I'll delete this little part here, and maybe some of these arrows too. Now, what if I called this x1 plus a? So I could do it the exact same way. F of x1 plus a minus f of x2 over x1 plus a minus x1 . Oops, sorry, that was x1 up there. x1 over a. Right. And that probably looks pretty familiar to you from the previous videos. And so that's the average rate of change. Now, sometimes this is called the average rate of change over the interval x plus a, well, I guess x1 plus a, x1. Now what about the instantaneous rate of change? I've got my x1 and I've got my f of x1, and I could write the instantaneous rate of change as f of x1 plus h minus f of x1 over h, but h is getting close to 0. And so to illustrate the instantaneous rate of change, one way we can think about it, or we've thought about it previously geometrically, is, and I know I haven't drawn it perfectly, and I don't know if I actually can with the graphing software that we're, oh, that's pretty good. The instantaneous rate of change is synonymous, geometrically speaking. This is the slope of the tangent line. And so the instantaneous rate of change, what is that? That's our derivative. So that's our instantaneous rate of change. Now let's find the relative rate of change using the instantaneous rate of change. So we want to find the relative rate of change at a very specific point. Maybe call it x1. Of course, x1 is associated with f of x1. And the slope at this point is going to be equal to our slope of the tangent line, which is the derivative. And if we want to know the relative rate of change, we can say it's the derivative of f of x at x1 divided by f of x. And that would be, analogous to the relative rate of change over an interval, where we might write f of x1 plus a minus f of x1 over x1. Should have had a 1 up there too. Now, it should be clear to you that if we want to get the instantaneous relative rate of change, or the relative rate of change of the instantaneous change, we need calculus, right? Because we can find over an interval, we can make an approximation, and we'll talk more about linear approximations when we get into chapter 7. We can do an approximation, but if we want to know the instantaneous rate of change, we want to let the interval get really, really small, which is like saying we want to let h get really, really small. We're going to need calculus. Here, the relative rate of change is telling us how much distance did the ball travel relative, in this instant, relative to its total distance traveled. So how far did the ball travel in the last very tiny sliver of time relative to the total distance traveled? Okay, so I hope the example using distance and time made a certain amount of sense to you. Now let's look at an economic example. How do we use calculus in economics? We're very interested in how things evolve and change over time. So let's take a look at the capital stock of a fictional country. So capital stock, so that's like factories, houses, apartments, all kinds of physical capital, apartment buildings, condominiums, all those good things, computers, all that kind of stuff. And we can see we got billions of dollars on the y-axis, and we've got time on the x-axis. So we're going from 1960 until 2020. And it's increasing. What kind of growth rate are we looking at here? It's increasing in what kind of way? Is it growing arithmetically? It's actually growing exponential. This is an exponential function. And you learned about exponential functions when you learned about the natural exponential. Now the question at the bottom is saying identify the instantaneous rate of change on the graph for 1980 to 2000, or on the graph for 1980 and 2000. So, without calculus, you might say, well, I've got 2 points on this line. I could take, I see that, oh, this looks like maybe it's 2200 there. This looks like, oh, maybe it's 900. And well, from 2000 to 1980, the change is 2200 minus 900, which equals 1300. And the relative change is going to be 1300 over 900. But we're not really interested in that. And the question also asked us about the instantaneous rate of change. And you can see that this is a curve. And so curves usually have different slopes at different points. Like say x1 versus x2. Or in this case, 1980 and 2000. So if we want to do this question properly, and so I'm going to erase that because that's not what we wanted to do. That's not what the question's asking us. We're going to find the instantaneous rate of change. How I would do that is I'm going to just identify the points of tangency. Right, and kind of hard to draw, but the slope of the tangency, or I should say of the tangent line, identifies the instantaneous rate of change. Because of course I can just write this as f prime of 1980, and I'd write that as the f prime 2000. And that's how I would identify the instantaneous rate of change on the graph for 1980 and 2000. And this graph actually shows me the rate of change in the stock of capital. So how is it changing over time? And we can see here that in 1985, the change looks like maybe it was, say, 51. If we go to 1980, looks like the change was maybe 45. And the rate of change is actually changing over time. So I could write the y-axis variable here as f prime of t. And since it's a function of time, This often comes up in macroeconomics, and you can kind of see if you've taken Econ 1010, this is a topic in macroeconomics. We could also write it with a dot above it to signify that it's a function of time. The little dot signifies a function of time. And that is our y-axis variable. Now here we have the relative rate of change in the capital stock. And notice that we've got a percentage on the y-axis. And I could write the y-axis. I've been using x, so I'll keep using x. And if I wanted to, I could put little dots on it because I've been using t. I could use t here as well, since the relative rate of change, like the capital stock itself, and like the rate of change of the capital stock, is a function of time. And you can see that it's, following this pattern, it's getting smaller over time. And the relative rate of change is sometimes called the proportionate rate of change. And you've seen proportions when you were studying Alex. In real numbers, proportions were introduced very early in that sequence. Let's take a minute to summarize. The derivative is the slope of the tangent and is the rate of change. And so usually that's f prime of x. The relative rate of change is the change in instantaneous rate of change divided by the function itself, or I should say by the value of the function itself. So we got f prime of x divided by f of x, or if you prefer, f of a. So x is taking on a value, right? And in this case it's the value a. The average rate of change is f of a plus h minus f of a, and this whole thing divided by h, which I showed you and derived for you previously. And in a previous video we saw that I'm going to change from x, which I'm used to the textbook's a. So you understand, hopefully you better understand that a is a placeholder. And the instantaneous rate of change is approximately equal to f of a plus h minus f of a. And that's what I showed you in the very first slide of this video. And just to be clear, in case you haven't seen it before, this is an approximation.